My name is Yaohui Wang. It's a great honor to be here today to present our work, Efficient Memory Overcommitment for I/O Passthrough enabled VMs via fine-grained page metadata management. This research was finished when I worked in the Alibaba group, and it introduces an efficient approach to achieving memory overcommitment for I/O Passthrough enabled VMs. First, let me provide some background on memory overcommitment and I/O Passthrough. In virtualization systems, the total memory allocated to a VM typically remains constant during its life cycle. However, the working set of memory within a VM is usually a subset of its total memory. As illustrated in this figure, the hypervisor allocates memory pages for the entire range of the VM's GPA, even when some memory is not actively accessed. This leads to inefficient memory resource utilization. Memory overcommitment helps to mitigate this problem. This figure shows how swapping-based memory overcommitment works. It reclaims inactive memory from a VM, stores the memory content to the swap space, which is usually on the disk, and reallocates memory to other VMs on demand. And for I/O pass-through, it is a technique that allows the guest OS to directly interact with the underlying hardware. Using I/O pass-through, a peripheral device can directly access the guest memory through DMA without the intervention of the CPU. It significantly decreases the overhead of guest I/O operations and is also required by the emerging high-performance RDMA applications. This makes I/O pass-through an irreplaceable part of virtualization systems like the public cloud. This figure shows the DMA mechanism in I/O pass-through. In the same way that the CPU MMU needs a page table to translate GPA to HPA, devices DMA requests rely on the I/O page table to translate IOVA to HPA. IOVA stands for I/O virtual address, whose space is usually the same as the GPA space. However, a natural contradiction exists between memory overcommitment and I/O pass-through. In memory overcommitment, the MMU page table entry and the I/O page table entry of the reclaimed page will both be invalidated after the reclamation. If the access to the reclaimed memory occurs at the CPU side, it will trigger page faults and traps into the hypervisor. The hypervisor will reallocate pages and fix the memory mapping to make sure the replay of the previously failed memory access succeeds. But if the reclaimed memory is a DMA buffer and a DMA request targeting this buffer arrives, there isn't a page fault mechanism on the device side to allow the hypervisor to reallocate pages and fix the memory mapping. So the missing I/O page table entry will cause DMA failures, which means the I/O operations will fail. To avoid such contradiction, today's public clouds usually choose to enable I/O pass-through to retain the I/O performance gain and sacrifice memory resource utilization by disabling memory overcommitment. Several solutions exist to address the problem. The first solution involves adding I/O page fault support to hardware devices, allowing peripheral devices to trigger page faults in the similar way the CPU does. However, I/O page fault requires dedicated hardware and is not widely supported by off-the-shelf devices. It also relies on memory swapping, which introduces significant I/O overhead. This is because reclaimed memory content is typically stored on slower storage media compared to the main memory. The resulting overhead not only slows down the hypervisor's response to memory reclamation requests, but also causes performance fluctuations in the VM and degrades its its service level objective. The second solution is to monitor DMA buffer allocations within guests. This approach involves two parts. First, determining if a guest page being reclaimed by the hypervisor is a DMA buffer. And second, notifying the hypervisor to fix the memory mapping in real time when the guest allocates the DMA buffer whose underlying page was reclaimed. vIOMMU and coIOMMU are two implementations of this solution. They are software solutions and do not require dedicated hardware. Nevertheless, they still face the memory swapping overhead, and coIOMMU needs extensive changes to the guest OS, which results in the guest OS compatibility issue. There are also some free page-based memory reclamation methods. They are free from the memory swapping overhead since there is no need to back up the contents in the free pages, but they are either not performance efficient nor DMA-safe. For example, ballooning is a classical free page-based method. It avoids DMA failures because it prevents the allocation of the reclaimed pages. So the reclaimed page is not unlockable in the VM until the hypervisor releases the memory to the guest. But ballooning suffers large guest communication overhead, which I will illustrate in the evaluation part. Except for ballooning, there are also other methods targeting free page reclamation. Free page reporting allows the guest to report the free pages to the hypervisor periodically. And the Hyperupcall allows the hypervisor to inspect guest free pages without guest intervention. However, guaranteeing DMA safety using these two methods is a challenging task. As this figure shows, the memory reclamation action in these methods is transparent to the guest, and the guest may allocate a free page whose underlying physical page is reclaimed as a DMA buffer. But the hypervisor will not be notified by this action. Thus, it does not have a chance to repair the memory mapping. So following DMA request addressing this page will fail and cause DMA failures. On the other hand, free page reporting faces the problem of timelessness. Its front-end driver initiates the reporting procedure with a fixed delay, which is 2 seconds in Linux implementation. So the hypervisor's memory reclamation request may fail even if there are unreclaimed free pages in the guest. Based on the above analysis, we have derived the design goal of our solutions. It should be DMA safe so that the memory reclamation and the passthrough can coexist. It should have hardware compatibility and guest compatibility to make the solution be easily deployed to existing systems. It should have low overhead. This not only decreases the hypervisor's reaction time for memory requests and enables the hypervisor to make more aggressive reclamation decisions, but also limits the performance impact on the VMs and guarantees high service level objective. This figure shows the overview architecture of vprobe. It contains 3 parts: the vprobe injector, the vprobe data manager, and the memory reclamation routine. The vprobe injector is a guest module. It only runs once after the guest finishes starting up. During the execution, it accomplishes 2 tasks: page metadata layout registration and helper function registration. This slide introduces the page metadata layout detection. In operating systems like Linux, each physical page has a corresponding piece of page metadata to record its usage state, for example, the reference count or the allocation status. And such metadata is usually organized statically and continuously in regions of the physical memory. The wave probe injector detects such layouts in the guest as several GPA ranges and registers this information to the hypervisor through the wave probe registration API. The helper functions gives the hypervisor the ability to parse the previously injected page metadata. Here are the two helper functions in our implementation based on Linux. The first function is page free. Its input is the struct page and the output is a boolean, which tells whether the page is free or not. The second function is page order. Its input is the struct page and the output is the order of the free page range in the body system. These two functions are very simple. What they do is to test the flags or read a specific field in the page metadata. The examples also show the compiled binary of the helper functions. The page-free binary contains only 5 instructions, and the page order binary contains only 2 instructions. With the page metadata layout and the helper functions, the hypervisor knows whether the guest page metadata resides and can pass the free status of each struct page without the guest intervention. The wave probe data manager runs in the hypervisor. It provides registration API for the wave probe injector. The registered helper functions and the page metadata layout information are stored here. It also stores the information of the reclaimed memory set. Since the hypervisor will directly call the helper functions via the injected binary, we need a verifier to prevent harmful calls. We use a rule-based software fault isolation method to implement the verifier. As I just showed in the last slide, the logic of the helper functions should be very simple. This simplifies the implementation of the security rules. I will not go through the rules in details here, but let me explain the principles of the rules and how they protect the hypervisor. First, the rules make sure the helper functions obey the convention of a function call, and no branch nor privileged instructions are allowed. Second, during the function call's execution, the accesses to registers and memories are strictly limited. These two principles imply that the instructions inside the call will be executed sequentially, and the execution will finally return to the caller. They also imply that the code will not corrupt any host memory. The memory reclamation routine is the core logic to reclaim free pages. Its execution is triggered by system events like periodical timers or memory pressure. After the preparation of the previous steps, the hypervisor can scan and pass guest page metadata to inspect the status of each page. And the reclaimed memory set in data manager will record the reclaimed GPA range, and it will also record the GPA range of the corresponding page metadata. The aim to record the GPA range of the page metadata is to avoid DMA failures. Here, let me explain how it works. The left is the memory mapping status before the free page reclamation, and the right is the memory mapping status after that. Note that after the page reclamation, wave probe not only invalidates the free pages mapping in the MMU page table and the IO page table, but also modifies the corresponding page metadata mapping in the MMU page table to read only. By doing this, when the guest allocates a free page whose underlying physical page is reclaimed, it needs to write the memory of the page metadata to change its status. This will trigger the page fault and the traps to the hypervisor so that the hypervisor can reallocate the pages for the accessed area and fix the memory mapping in the MMU and the IO page table. One challenge for the reclamation process is the synchronization problem. The guest may allocate the pages while we are reclaiming them, and the status of the page metadata may change from free to allocated within the memory reclamation routine, which may cause inconsistency in the system. Here we use double checking and mutex to avoid the racing conditions. The figure shows this logic. After a vprobe detects a free page, it will first acquire a mutex, then make the struct page GPA range to read only. And next, it double checks the free status of the page. vprobe will reclaim the page only if the page is still free in the second check. These two figures are the two cases of the racing conditions. The green part is the hypervisor's reclamation logic, and the yellow part is the hypervisor's page fault logic, and the blue part is the guest memory allocation logic. In reclaim 1, if the guest allocates a free page after the hypervisor makes the struct page GPA range read only, it will trigger page faults, and the mutex will prevent the page fault handler to fix the memory mapping before the hypervisor finishes reclamation. This guarantees the atomicity of the memory reclamation process and the page fault handling. In reclaim 2, if the guest allocates the free page before the hypervisor makes the struct page GPA range read only, the double check will detect such behavior and skip this page, so as to avoid the inconsistency of the page status knowledge. Now comes to the evaluation. Here are the experiment settings of our evaluation. The experiments are based on the hardware architecture of the Intel CPU. The hypervisor is based on coIOMMU and KVM, and the hypervisor manages the host memory in 2 megabytes granularity. The guests in our experiments run Linux OS and each equipped with 2 CPU cores and 4 gigabytes main memory. The storage media we use for memory swapping is a hard disk drive with 250 megabytes per second I/O throughput. First, we evaluate the operation time cost to reclaim or reallocate a 2 megabyte page. For ballooning, it relies on the communication with the front-end driver running the guest. The communication introduces a large delay, especially when the guest is busy with CPU-intensive tasks, which reduces the chance for the thread of the front-end driver to gain CPU time slice. For I/O pass-through, it relies on memory swapping, which introduces a large overhead of disk I/O. And for vprobe, it significantly outperforms the other two methods. It takes only 90 microseconds to reclaim a 2 megabyte page and takes 60 microseconds to reallocate the page. We also evaluate the efficiency of vprobe using micro and macro benchmarks. The micro benchmark includes TCP throughput and the UDP latency, and the macro benchmark includes the Redis QPS. We compare vprobe with the baseline, which does not reclaim any memory from the guest, and with the IOPF-based method. This test evaluates the performance impact of the memory overcommitment method in cases when a large amount of memory is reclaimed from the guest and the upcoming workload has high memory footprint. At the beginning of these benchmark tests, we reclaimed 30% of the server's memory, which is an extremely high value in practice. And the benchmark workloads are customized to make sure they have high memory footprint during the test, so that they can trigger page faults and the memory reallocation logic. As this result shows, the performance of vProbe is only slightly lower than the baseline, and it is much better than the IO page fault-based methods. And people who are interested can refer to the paper for more details of the experiments. And at last, let me conclude the work by reviewing the 4 design goals. First, DMA safety. vProbe proposed the novel fine-grained page metadata management to avoid DMA failures, so that memory overcommitment and IO pass-through can coexist. Second, hardware compatibility. vProbe does not rely on IO page fault, which is not commonly supported by off-the-shelf IO devices. It only relies on basic virtualization features of the CPU. These features are widely supported by popular CPU platforms. Third, guest compatibility. vProbe does not hack any API of the guest OS, while in this paper, we examine Linux-based implementation of vProbe. And the adoption of vProbe is similar in Unix-like operating systems like the FreeBSD that use a similar memory management mechanism to Linux. Fourth, low overhead. vProbe does not rely on memory swapping or guest communication. The experiments show that vProbe achieves extremely low overhead, and it achieves near baseline performance in the benchmark tests. There also exist 2 limitations of our work. First, this paper defines and examines an example implementation of the vProbe design that is specific to x86 architecture and the Linux-based OS. Therefore, architecture-based and OS-based assumptions of this example implementation would need to be adjusted when moving to other architectures and OS types. Second, when reclaiming free pages, vProbe needs to modify the memory mapping for the page metadata GPA range. But since memory mapping is by the granularity of pages, the metadata should reside on the same physical page, so vProbe can only reclaim continuous free pages in batches. As a result, guest-free page fragmentation may weaken the reclamation effect of vProbe. But free page fragmentation in the guest is usually caused by high memory pressure, which suggests the system not to reclaim memory from them. Also, this problem can be mitigated by the memory compaction functionalities in the guest OS. So that's the end of my presentation, and I'm online for the upcoming Q&A section. And for further questions, you can contact me using this email. Thanks for listening.